Hello, and welcome to today's ACM SIGSOFT webinar. This webcast is part of ACM SIGSOFT's commitment to provide value to its current and future members. The ACM SIGSOFT webinar series features speakers from the Future of Software Engineering track at the International Conference of Software Engineering, as well as select keynote speakers and distinguished paper authors. I am Bradley Schmerl, Principal Systems Scientist in the Institute for Software Research at Carnegie Mellon University, and it is my pleasure to welcome you today. Before we get started, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. First, the slides will advance automatically throughout the event. On the bottom panel, you will find a number of additional widgets and resources. If you're experiencing problems with the slides or audio, press the F5 key in Windows, Command R if you're on a Mac, or refresh your browser on a mobile device, or you can close and relaunch the presentation. To control volume, adjust the master volume on your computer. At the end of our presentation, we'll have time for questions. Please type your question into the Q&A box at any time during the webinar and click the Submit button. This session is being recorded and will be archived. You will receive an automatic email notification when it becomes available. Today's presentation is Engineering Smart Cyber-Physical Systems by Danny Weyns from Linnaeus University and Tomas Bures from Charles University. Danny Weyns is a professor at Linnaeus University, Sweden, where he leads the AdaptWise research group. From October, he will be affiliated with Distrinet Labs at the Catholic Universiteit Leuven in Belgium. His main research interest is in software engineering of self-adaptive systems, where he is studying formalisms and design models to realize and assure self-adaptation for different quality goals. Tomas Bures is an associate professor at the Faculty of Mathematics and Physics, Charles University in Prague, Czech Republic. He is a chair of the Department of Distributed and Dependable Systems. His current research focuses on component-based modeling, software architectures, and multi-paradigm modeling of smart cyber-physical systems. Danny and Tomas, we look forward to your presentation today.
Welcome to everybody. So in this webinar, we will talk about software engineering for smart cyber-physical systems. This talk is partially based on the outcome of a workshop that we organized on this topic at the last ICSI conference. So the aims of the webinar will introduce you with the notion of smart cyber-physical systems, and we will look into challenges that they pose to software engineers. We will look from the workshop outcome to some key themes that were discussed at the workshop related to software engineering of cyber-physical systems. And we will highlight open research topics that have been identified during the workshop. So the outline of the talk, we will start with motivating why we need to discuss this material. And then we will give a short overview of how we organized the workshop, and then zooming into the core of the talk here. First, the different themes that have been discussed during the workshop, and then the research topics that have identified. We conclude with wrapping up, and then the floor is open for questions and answers to that. So for motivation, we start with a more general question: what are cyber-physical systems, for those of you who are not familiar with it? And then we will look into what makes it smart cyber-physical systems, and why are they so important, these kind of systems. Of course, then the obvious question for software engineers is, why are traditional software engineering approaches not sufficient to deal with this kind of technology? So to start with cyber-physical systems, actually in the past decade we have observed a trend towards integrating computational and physical elements increasingly. Think about the embedded systems, think about mobile systems, for example. The vision of cyber-physical systems is depicted there in this figure here, and it shows us all kinds of visions in a way. You can see persons with personal health assistance. You can see on the back a smart city where you can imagine intelligent traffic. You can think about the power grid. And what is key in these kind of systems is that there is a kind of ubiquity devices, of computing devices, and they are all somehow connected with one another and affecting each other. So looking at a bit more from a technical point of view, cyber-physical systems are systems of collaborating computational elements that are actually controlling physical entities. And this control is typically involving feedback loops. Now, what makes cyber-physical systems really distinct from traditional software engineered systems is the fact that this involves multiple disciplines. So the different layers of the technology stack are involved and requires expertise from different disciplines, including physical things, electronical and electrical disciplines, communication over networks or wireless, and eventually software. And within the software, we of course have to deal with different subdisciplines, including real-time sensing, signal processing, and distributed decision-making, self-star features, and so on. So now, what makes a distinction between smart cyber-physical systems and, you can say, regular cyber-physical systems? Actually, there is not really like a difference. What we want to emphasize here is that we want to look at cyber-physical systems with smartness on board. And basically, it has to do with systems that are equipped with some kind of intelligence. And that intelligence is required to deal with the conditions under which these systems have to operate. In particular, all kinds of dynamics. And this involves, as we will see later on in this talk, a lot of uncertainty. So basically, it's about interconnected and collaborating systems that are equipped with smartness on board to deal with the dynamics. Actually, these systems are important for a variety of reasons, but mainly because these kind of systems are considered as the type of systems we need to deal with a number of really challenging issues we see in our society, including environmental and other society challenges. And then we think about smart energy, smart mobility, ambient assisted living, and so on. Now we have different, we can look at the smartness from different perspectives. Actually, different people have looked at it from different perspectives, and we in this talk we will give a few of these perspectives. A few of these examples. The first thing you see here is a model proposed by Lee and his colleagues, what proposes a 5-level model, and it is in the context of the Industry 4.0 originated in Germany that this model has been proposed. And this model looks at a really torrent level. So let me start with the bottom layer, where you see, in fact, the connection level. It has to do with sensors. So there at that level, we are looking at the basic monitoring features. And the smartness there has to do with the fact that if you think about the long living systems, as many of these systems are, there should, for example, be support for plugging in and plug and play support for new sensors in the future. At the next level, the level above, we think about the machine level, and there we think about conversation. So it's about analytics, to transfer the data that sensors have collected into meaningful information. On top of that, we look at the cyber level, and there we are thinking about integrating and correlating data, so typically by using models specific for this kind of features. At almost the next to top level is the cognition level, and there we are going rising up to the level where the system is interacting with people, and this requires a further synthesis of the information. Typically also in terms of providing visualization for people, probably including simulations of the system. And at the top level, it's called the configuration level, and there we talk about the self-start properties. So property for the system allowing them to adjust or to correct or optimize themselves autonomously, possibly with intervention of humans when needed. Another way to look at the notion of smartness, you can see that here in this cyber-physical convergence proposed by a number of researchers a few years ago. And there you see that these authors, they connect the physical layer, the entities and the links at the physical world, towards entities and links at the cyber world. And if you think about the kind of physical world they are looking at, this raises a number of challenges. For example, just a few of them. If you think about one of these entities at the cyber level, they might require a kind of comprehensive situation awareness, which might require thinking about a larger scale of systems, the need for local autonomy. Another issue here might be this type of environments in the physical world will give rise to a lot kind of uncertainties, where people are involved in creating things that are difficult to predict. And of course, this uncertainty is transferred up to the cyber layer, and then you have to handle this kind of uncertainties. A third example is closer to Bradley's world. Here is the well-known framework, Rainbow framework, what can be considered as a prototypical realization of self-adaptation. And in fact, there a system is equipped with a feedback loop, and this feedback loop enables a system then to deal with changing operating conditions in an autonomous way. So also there you need all kinds of smart features to enable this system to adapt autonomously. Finally, a last example it comes from the world of self-organization. In this line of thought, the people consider, instead of traditional static architectures, they are looking at really dynamic configurations of groups of entities, what are called in one of the EU projects that is mentioned on the slide, ensembles. And often the mechanisms that are used to group and regroup the different entities are inspired by principles from nature, stigmergic principles often. So let's now look at why traditional software engineering approaches are not really sufficient to deal with all these challenges. Well, if we look at the properties of the software systems, as I mentioned them before, we can identify different type of challenges. One of them is that we see like a kind of blurring boundaries between the hardware in these systems and the software. We cannot really design software just ignoring the hardware or the effects on the hardware. There is an inherent uncertainty in this type of systems that should be considered really first class. And the scale of the systems, if you think about the initial picture I showed, where you have a smart city, so the systems often they grow to a large scale, which raises a lot of complexity that goes beyond the traditional type of systems we have experience for to design. And a very important part is also the role of humans in general and end users in particular. In this type of systems, think about an intelligent traffic system. Humans have a very prominent role in the way the system is behaving and evolves. Another very important property is the open-endedness of these systems. Again, think about a traffic system. People come and go all the time. So this system should be conceived in such a way that it can handle with this kind of open-endedness. Often there is also a very strong notion of locality in terms of physical position of entities, which is also something that has to be dealt with. You see, there are many different type of properties that make these systems really challenging to design. Now, as I said before, engineering these systems, given the fact that they cross-cut the different layers of the technology stack, it requires expertise from a variety of fields. And what we see, of course, today is that these fields are fragmented. The experts in the different fields are hardly talking with each other. And even within the software engineering field, we have listed there a number of subfields that are typically relevant in this area. There are even subfields that are fragmented among each other, and there is hardly any discussion or sharing ideas between them. Now, the properties of the kind of systems we talk about, they really require to go beyond the classical layers in the technology stack As an example, if you think about adapting these systems, or if we think about different layers of the stack, you can adapt at different layers, but of course it will affect the way the system behaves, and we need in another way to look at adaptation, looking from, it's something that cross-cuts the different layers. So then the fundamental question is now, how can we combine the expertises in such a way that, that we can build these systems in a trustworthy way? So to deal with these challenges, or let's say driven by these challenges, Tomas and I and two other organizers started with this workshop on software engineering for smart cyber-physical systems. And basically the goals for the workshop we have put forward were, first of all, trying to understand the problems, to get a better grip on what are the problems in software engineering of these kind of systems. Then we want to study the underlying principles that provide the foundation for engineering these systems. And among them are, for example, how to handle uncertainty, how to reason about uncertainty. A particularly challenging thing is how to deal with emergent behavior. If you think about a large-scale system with decentralized control, the behavior of such system is very difficult to predict, and then how to keep the system behavior within certain boundaries. Another fundamental problem is distributed control, which is still today an open research challenge in general. So there are a number of things that need to be further studied. And finally, the workshop also aims to identify promising solutions at the end, and then we are thinking about what about modeling these kind of systems? What kind of engineering processes can we think about? Clearly, this is like a multi-stakeholder, multi-ownership problem, so there will be new processes required. Integrated VMV is a challenging problem if you want to give any guarantees about the behavior of this system, type of systems. So the first edition of the workshop, as I said, was organized at the last ICSI in Florence. Just for the record, we got 19 submissions for the workshop, and 10 of the papers that have been submitted were accepted. Briefly, in the morning session, we had a keynote talk from David Garland at Carnegie Mellon, professor at Carnegie Mellon University, and we provided floor for the participants, in particular the paper presentations, short presentations. And then the main part of the workshop was actually in the afternoon. The morning was just prepare the floor for the afternoon, where we had discussion groups, and then at the end, discussion in a plenary session. So I will start with, as I said in the beginning, we will first look into the themes that were discussed at the workshop, and these themes were mainly driven by the papers we received, and then afterwards we will look into the challenges that came basically out of the discussion sessions in the afternoon. So the first theme is about modeling challenges, and it is basically inspired by the talk David gave during his keynote. So as David pointed out, consistency and completeness of cyber-physical systems is a very challenging problem, thinking about the fact that we're talking about this cross-domain issue. So existing approaches are hard to model in a consistent and in a complete way a system that cross-cut the different layers. If you don't have good models, then it's difficult to analyze and give any assurances or guarantees about completeness or consistency. And another important point made by David was the integration of humans, as we traditionally in software architecture, for example, are not really taking humans into the modeling as first-class entities. So David elaborated on the way they are working on that, and actually his proposal was to put software architecture as a kind of central unified artifact to deal with the engineering challenges. And in fact, it's not surprisingly if you see that software architecture and software architects in particular have been always been the bridge that bridges different stakeholders in engineering software systems. And in this case, of course, if we think about cyber-physical systems, software architects should also bridge not only stakeholders but also disciplines. And the last point about stochastic multiplayer games, David explained in his talk how to deal with humans in the loop, and proposed there an approach based on these games to deal with that. So then the second theme of papers were about faults and conflicts, and in fact this has all to do with the fact that we need consistency, and consistency of cyber-physical systems is a really multifaceted topic. You need to, there are the different papers that we are looking at, that we hear there, they are looking at different aspects related to that. One of was a localization of faults in models. And then, of course, given the fact that there is uncertainty, there might be used, the authors propose statistical models for modeling behavior, and then based on traces of the behavior, they could identify faults in the behavior of the system. Another level of conflict identification is cooperation of cyber-physical systems. So in that sense, cyber-physical system consists of many interacting entities, and there might be conflicts among entities, and then you have to deal with these. And the authors in one of the papers proposed there to use metadata, to add metadata, and use that to handle the conflicts in an automatic way. Finally, there was also a paper presentation about specifications, or when conflicts in specifications when the cyber-physical systems evolve. And given the longevity of these systems, evolution is a natural element of it. And the fact was there that they were looking at versioning and how to link artifacts, engineering artifacts, taking into account versioning. They actually proposed to extend versioning beyond the traditional versioning of software, and also looking into the artifacts that are used to deal with the engineering itself. Then there were a session about modeling, testing, and verification. And this session has again to do with the dependencies that cross-cut across the technology stack. So first of all, there are a variety of uncertainties. Uncertainty is a very multifaceted element. They can come from different elements. They can come from censoring information. They can come from the uncertainty in terms of sensing information. They can come from models that are not accurately representing data, or it is impossible to represent the information accurately. It might also go farther in terms of you build the system, you deploy the system, the goals might evolve, and at the moment when you were designing the system, it was difficult to anticipate how these goals could evolve. Nevertheless, the system cannot go down, and you need to handle this uncertainty. Then there was also another talk about the high-level application requirements versus resource-limited microcontrollers. And again, this shows the fact that you are going from very low levels, where you are close to the hardware or at the hardware level, up to the high-level application requirements, and then how to match these different worlds. The last paper we got in this session was a very interesting empirical study that actually was looking into how software engineers perceive the use of tools and techniques for testing, verification, and validation of cyber-physical systems. So there were a lot of interviews with software engineers about the perception, how they perceive the existing tools. And the main outcomes of this study were that software engineers, they consider traditional testing approaches as not sufficient enough in terms of rigor to detect errors for cyber-physical systems. They identified that engineers were really more as expected interested in using formal methods, however, to verify properties. However, they were disappointed in terms of the support that the existing tools provide, both in terms of expressiveness and in terms of intuitiveness or even efficiency, well-known scalability. And then finally, also identified that existing simulation tools are not really prepared to deal with the challenges of integrating cyber and physical elements as a support tool for verifying properties of systems. Then the last topic of the sessions was on collaboration. So collaboration has to do with the interplay between elements in a cyber-physical system. And one of the papers identified the fact that that this interplay, if you want to do analysis of it, if you want to understand how the system behaves, or even if you want to do at runtime things, you need to work at the instance level. And it is something that is often not really done very well in current practice. If you look at software architecture practice, we are very useful to work at type levels. We document we document components at type level and their connections at type level. However, we are rarely looking more into scenarios when it comes to instance level. However, in cyber-physical systems, there is a need to look at this instance level to really get understanding about the system or give guarantees. And this is particularly challenging if you think about the heterogeneity of cyber-physical systems in terms of the type of entities that interact, the distribution of the system and decentralization of control in the system, and also, as we mentioned before, the openness of the system where entities can come and go at any time. So let's now move to the research challenges that have been identified during the workshop, and they followed more or less the understanding of the concepts we saw and turned into what we're looking at. Really are looking at what were the concrete issues to resolve the different problems we identified in the teams. So there were 4 groups that were looking at different types of research challenges. The first one is aligning different disciplines. So the second group was how to deal with humans in the loop. The third topic was initially pragmatic versus systematic engineering, but it turns out that it was pragmatic and systematic engineering. And the last topic has to deal with was on uncertainty in cyber-physical systems. So the first research challenge relates to the topic that has been mentioned here a few times already, how to align different disciplines. And you see there in the example that different disciplines have to interact with each other. Software engineers with control engineers, with mechanical engineers, you name it. And typically, one discipline looks from its own perspective and might put some kind of abstraction of the other disciplines within his own understanding. Given the fact that we need to integrate disciplines, the general understanding during the workshop was that we have to understand each other and learn from each other. And in particular, we should take an open-minded perspective and respect each other as a discipline, each other in his expertise. Every expertise, of course, every discipline has its own proven expertise, and it is important that we respect that for each other. It might sound like a bit strange, but it is often an issue that when you talk with people in this field, that there is like a kind of minimalization of the expertise or the relevance of another discipline. Of course, if we want to talk with each other and understand each other, we have to think about what language do we use to talk with each other. It's a language issue. What vocabulary do we use when we express information from our own domain to another domain? And it's important for research to understand what is a good vocabulary for that. As David was telling in his keynote talk, we might start from software architecture as the central vehicle around which we build things, but obviously mechanical engineers, they have their own view on the world, and it is and it has to match with that. Control engineers the same. There has recently been a lot of interaction between software engineers and control engineers in the world of self-adaptation, and these issues of mismatching vocabulary is a prominent issue there. Another important aspect in terms of understanding each other is also understanding what assumptions are different disciplines making. So we have to handle these different facets. What was proposed during the workshop is in fact in line with one of the paper presentations that I was mentioning before, is really first to understand. And empirical research could help to understand a bit better what is the world of cyber-physical systems. So if you think about there is an alignment problem of disciplines, then we should investigate to what extent is there a problem. To what is there awareness or is there lack of alignment within the world of cyber-physical systems? And if there is a lack, we should identify how big is that gap and exactly what is the problem there. Where are the things that are hampering disciplined engineering practice? We even should ask ourselves the question, is there really a need for alignment? And if so, then of course we have to identify where. What we think is a very important facet here, also from an academic point of view, is what is the role of education in this all? If we say we have expertise in different disciplines, and now we need to deal with cross-cutting issues, then the obvious question is, do we need to educate people that have this cross-domain knowledge and that they can serve the role of being familiar with the expertise that is required in the different disciplines. Another challenging aspect is humans in the loop, as we have mentioned before. So in cyber-physical systems, there are different types of people involved. You can think about engineers, of course, that are creating and adapting and evolving the cyber-physical systems. And these engineers are different to many other systems. They are like, think about a multi-ownership domain where you have engineers working within their own domain, but they have now to work together or to align with engineers in another domain. And then I'm not talking about the vertical domains, but I'm talking horizontally. So this is one challenge. End users are obviously involved in the loop. So then we might think about how do end users use that system? What do they need to know, and what about the state of the system? How to handle changing requirements, and how to involve humans in that sense. Another type of humans that are affected by cyber-physical systems are those that are system external. They are not involved directly in the functionality of a cyber-physical system, but they might be affected by it. Think, for example, you have an autonomous driving system, but people on the street, they are somehow involved in the way the system behaves, and that will affect the cyber-physical system. So actually, people in general are a source of uncertainty in this system, and then in particular, those people that are external to the system are part of this uncertainty, and they are important as they might be affected by the system itself. So then finally, we should look at how to handle the awareness of changes. So if humans are involved in the loop, there is of course a whole issue about to what extent do we have to involve people. So what should be like a notification model? It might be risky to involve users about certain, or humans about certain properties, in particular users, or it might be exactly the opposite and be necessary. How to involve the humans in decision making, when to involve them, and in what way do we have to involve them? What kind of feedback do we provide to the cyber-physical system in terms of input from humans? In general, there is an underlying issue here, is that the cyber-physical system, if it becomes smart, it has knowledge. Of course, this knowledge is internal to the system, and then if we have humans in the loop involved, then to what extent do we know what the system knows, and to what extent do we have to know what the system knows? So these are raising fundamental challenges. So then to what are the effects of changes and end users introduced to the cyber-physical system? So there are a variety of things that have to do with changing the cyber-physical systems and the role of humans in the loop. For example, one of the things might you want to change it, humans might want to change to new requirements, but of course it has a cost. And then the question is, are we equipping the cyber-physical systems with features to make some kind of prediction what the cost will be for that? And how can we inform users about that to let them decide whether they want to apply these new requirements or not? Another issue in terms of changing things are to what extent are cyber-physical systems depending on capabilities of humans in terms of providing input. So is the cyber-physical system really dependent on the input of users, or it can tolerate certain lack of capabilities of humans? Finally, and related to that is if humans would provide bad user input, how would that affect the cyber-physical system? Can it handle bad user input, still assuring that the system is operating in the way it should operate, or at least should operate in a sufficient, efficient way? So these are all posing fundamental issues to how we engineer these systems. Then the next type of challenges has to do with the way we engineer this system. So the first question is, what type of engineering practice do we aim for here, or do we need? Are we looking at a more pragmatic engineering approach, or do we need a more systematic engineering approach? And actually during the workshop, it turned out that we need probably a combination of pragmatism and systematic approaches. One of the key things there is the mismatch, a mismatch problem that typically exists in cyber-physical systems. You have on the one hand domain experts, and you have on the other hand software engineers. And it's common that domain experts start to build a system, but then at some point they run into trouble, and then software engineers are called in to deal with the trouble, to deal with the problem and solve it. Of course, then the software engineer has to become familiar with the whole domain, and it's not optimal. So there is in fact recently some interesting evolutions towards really starting in terms of interdisciplinary teams that involve domain experts from the outset if you start building these kind of systems. Another issue in terms of pragmatism versus systematic engineering is to what extent can we really exploit and rely on smartness? To what extent can smartness help us to tolerate things? So a system as complex as we are talking about is inherently, it inherently has a few issues. There are always some flaws. And then to what extent can smartness help us to deal with these inherent issues and allow the system in fact to keep working in a satisfactory way? Another very important aspect in terms of composition of systems. When we talk about composition, we talk about the fact, for example, that we are in an open world. In an open world where entities can come and go. It's difficult to deal with that in terms of modeling, for example, to deal with that in terms of assurances, in terms of evolution. So open-endedness should become a first-class aspect of modeling and engineering these kind of systems. And in particular, if we want to think about consistency and security, these are very challenging problems. Finally, we believe there is a need for a kind of seamless integration of design time and runtime activities. So the traditional way to look at software where we design software, develop software, deploy software, and then let the system work at runtime. As soon as a problem arises, it comes back to the engineer. Is now something that we have to move into a world where these two activities are integrated with one another. The fact that we have uncertainty raises the issue of we cannot design with full understanding and full knowledge the system, and so certain facilities have to delegate it into the runtime, and then the system should support adaptation at runtime to deal with these uncertainties. So we have talked about some certainty in a number of slides here today. And here we list a number of these challenging things we have to think about when we talk about uncertainty. We have spoken already about goals and requirements. They might change while the system has to keep functioning. Obviously, there might be uncertainty in terms of the environment. The resources that are available might not be available as expected. Nevertheless, the system should deal with that in a way. We might think about modeling uncertainty. Maybe we have to make abstraction of things, and the resolution of the abstraction might imply automatically a certain lack of might introduce a certain level of uncertainty. Behavior uncertainty, as we said before, humans in the loop automatically introduce their behavior might be not as expected. The emergent behavior of systems where control is decentralized, and even that uncertainty might raise from the adaptation of the system itself. We might adapt the system, but maybe the adaptation itself is not fully controllable. Maybe we don't know exactly how long it will take before a certain adaptation will be effected. So it introduces another type of uncertainty. So you see uncertainty, it should be clear that it is a concern that has to be dealt with from the outset, actually. And the discussion at the workshop, in fact, evolved towards a runtime adaptation. So we need, for runtime adaptation, we obviously methods how to monitor the system, and then how to analyze, plan, and enact the changes. And the idea that was raised at the workshop was a kind of perpetuability perspective on engineering. So we start the design in terms of we are flexible in the design and keep certain design decisions we cannot make due to uncertainty. We postpone them and we build a system to let it handle at runtime when the knowledge is available, which implies that the system adapts when the knowledge becomes available. If the system then faces an issue that it cannot handle, then it returns to the engineer, and then the engineer can have a look at it and can deal with it, and then evolve the system and deploy online the evolved system, and then the system again can, with its new features, adapt whenever it is needed, and if it faces a problem, it returns to the engineer, and you get this kind of perpetual approach where the human and the system are interacting with each other continuously over the lifetime of a system. So to wrap up here, what we have said is that these smart cyber physical systems, they are a very important evolution that we notice, and they are important. They are important because these kind of systems are required to deal with different environmental and societal challenges that we face nowadays. On the other hand, although they might be necessary, they are not obvious to build. Actually, they are very challenging. And we have presented here a number of aspects and challenges related to these aspects for software engineers. The key observations that we have seen from this from the workshop are that engineering these type of systems requires a really truly multidisciplinary approach. We can really no longer escape on the fact that we have to sit together with different disciplines to deal with the problems these systems pose us. It's important to consider humans here in this engineering of these systems truly as a first-class player. And actually, the dominating aspect in the engineering here is uncertainty that cross-cuts everything. The system is continuously subject to change, and that introduces uncertainty that we have to handle from the outset of engineering these systems. So we see a number of long-term challenges here, and the first one is to understand how to align the disciplines. So we need to think about what are languages, what are the type of models and methods we need to engineer this system, and then how can we handle this? Then as I refer to this perpetuability of the engineering, we have to understand better what does that imply. How can we realize this perspective to engineer smart cyber physical systems? And finally, we believe that it is very important that we don't postpone the fact that we should define some prototypical applications, exemplars if you like, that allows us to drive our research, to evaluate and compare the new things we develop, the methods, the techniques, the tools, and so forth. And the workshop that we have organized last time at XC, we aim to continue with it at the next conference, is in fact aiming to create a forum to at least to contribute to make this possible. So the last slide here will list a number of resources that those of you who are interested can find online. And the proceedings of the workshop, there is a link there. And there are a number of resources from the presentations, from the workshop, that you can also find online, the link at the bottom. So that concludes my talk. I leave now the word to Bradley to start with the questioning and answer.
Thank you, Mr. Weyns. Our first question is related to testing. So the question is, how can these kinds of systems ever be tested? And if we're thinking about trying to design the systems with testability in mind, can you outline any challenges that we might have?
Yeah, thank you, Bradley. Well, basically, from the perspective of the testability, we have to understand how the CPS are structured. So on the bottom, the CPS are sort of the traditional embedded and real-time systems, but then going on the top and going up, the systems basically start to be composed. They are sort of systems of systems, and then in a smart CPS we can also somehow imagine to have an analytics layer or some big data processing layer, and often when we see like what the different industry understands under CPS, they also see, for instance, cloud computing involved because much of this analytics computation is like so heavy that it doesn't really make sense to execute it on the level of the embedded devices. So from this perspective, we have to understand that the CPS is actually a stack of technologies where we start with the embedded devices where, for instance, the real-time matters very much, and going up maybe to devices which are more like components of the shelf, which could be like normal PCs or normal servers, as we know from Intel, etc. And going up where we can easily reach really the cloud and cloud computing. And so when speaking about testing and the testability of the CPS, we kind of have to combine the testing at these different levels. So on the very bottom level, I would say the testing and testability has really to point in the direction as the embedded systems and the real-time system have been tested traditionally. And there I think that from making it like testable, we can very much look into the model-driven approaches which are long known, and I would say every engineer somehow familiar with simulating would know the different like simulations when you can have the processor in the loop or the hardware in the loop and software in the loop, etc., which I believe provides very good methodology even into how to test the system as it is being developed, so that there are no such a big surprises when it comes to the real hardware. Then of course the testability of then of course we have the communication and then we have the data aggregation, where probably we could imagine some approaches to testability as we know from networks, and then going up we probably would have to look into some testing approaches that we may know from cloud. But the thing is that all these things actually have to be treated together. And another difficulty here is that typically we have to have some particular environment in mind. So I believe what will be needed for CPS to allow for testing, and that will be basically we will need to have good simulators. This is also because the CPS are supposed to be or will be or are heavily distributed systems, and we know from our experience that testing a distributed system is a bit of nightmare. We kind of need artificial environments where, well, environments which are close to reality, but still where which we can easily scale up, so that we don't really need to employ 10,000 people just to test the system, but that we can somehow test it on a server farm and get comparable results. And from what I have seen so far, there are pieces which can be combined. So, for instance, we have state-of-the-art network simulators, could be NS or could be OMNet++. We have simulators which simulate mobility. We have simulators which simulate, for instance, different domains. So, for instance, you would have a simulator for traffic like MatSim, where you can really simulate the traffic in urban settings. We have simulators for physics and the dynamics of the systems. But I would say the challenge will be really to be able to somehow put together all these simulators in some more comprehensive manner, so that we could really reason about the different levels that Dennis spoke about, so that we can reason about them all together and still get some results which would be representative, which would reflect the reality. And of course, coming to this, reflecting the reality, maybe this could be also helped by having some computational models, which are kind of which are more friendly to the testing, or more friendly to the simulation, so that they really ensure that the results in simulation are close to results which we can get into reality. So I would say we have to really imagine this whole span, and then like seeing the testing on the individual levels, but then seeing it all together, and that, in my view, is a challenge. I don't think that there is or I haven't heard about any solution which would be really able to provide satisfactory results in this field. Thank you.
Okay, thanks, Tomas. One of the audience members had the comment that we maybe need more precise ways of describing behavior of physical systems in a way that makes sense to software engineers. But the more general question that they had was, is there a need for some kind of alignment between all these different models? And if there is a need for alignment, at what stages and in which models should the alignment be done?
Yeah, thank you. Well, definitely the alignment is what it calls for. We can actually see it like coming from different disciplines. Actually, all the different examples that we were, of the notion of smartness that we were showing at the beginning, and also what we can hear as the experience from industry or kind of what's coming from the different disciplines. It is essentially a desperate call for alignment. So in a way, the alignment is needed, and we see it very much. As for particular means for the alignment, again, it somehow we still could see that the scientific community and basically the practitioners community here is quite fragmented. So typically, people build the alignment or kind of try to align the models. They appreciate the diversity, and then they try to somehow unify it under an umbrella that they know. So, of course, what we see in the field of software architectures is that the people are trying to use software architectures, which is, for instance, very much what David Garland was presenting where the Acme and Acme Studio is used to somehow represent and bring together the models. And and then, of course, if we speak about MDD or if we speak about UML, then we can again see like the different spin-offs UML, like SysML, where models or where the things are tried to be like captured the same way. So, but on the other hand, I couldn't really say that there has been a single winning solution on the model alignment. So though it's very important and we can't possibly survive with that, I've not seen it, and then I would say this is again quite a challenge. Was it an answer, or is there anything I forgot about?
No, I think that's fine. Thanks, Thomas. Yeah, I mean, I think it's safe to say perhaps we're at the sort of early stages of this, considering this work. There was a session in the workshop on modeling, testing, and verification, and one of the participants had a question about whether any of the papers discussed compositional approaches to modeling, testing, and verification. Okay, it seems like we have lost connection with...
yeah, sorry, Bradley. We are back again. Sorry, we just got disconnected. No problem. So we are back again.
Okay, so one of the participants was asking about the modeling, testing, and verification session, and wondering whether any of the papers discussed compositional approaches to those things.
Well, actually, they did. We had one paper which was looking into how the system can be decomposed so that its particular properties can be verified, which I think was the paper by Professor Podgórsky, and quite a few of them were also aiming in this direction. Essentially, what we can see in this direction is that the verification by itself is quite difficult. The verification or any formal analysis in the CPS, which are more open-ended, is even more challenging, and especially when we start combining the discrete and continuous word, because then sometimes it's heading in the direction of the hybrid systems, where the knowledge is even less than there is for classical discrete event-based systems. And of course, one of the main approaches to tackle this explosion or to tackle this complexity is partitioning. The very nice thing about CPS, and I think this is something that has not been really so much utilized so far, but I think it has to be, is to utilize the principle of the locality, so that the things which are close to me in the physical world are more important and are probably going to influence more the analysis than anything else which is on the other side of the world or in another city. So to make it brief, it has been discussed. It is important, and I would say there is still quite a lot of potential in making use of the good specifics of the CPS to make the analysis much easier, so as not to handle it in a general case, but to handle it with the specifics of the CPS.
Okay, thank you. I'm afraid we've run out of time today. I'd like to thank Professors Weyns and Bures again for their informative presentation and insightful answers to the many questions. Special thanks to each of you for taking the time to attend and participate in today's webinar. This webinar was recorded and will be available online in a few days at www.sigsoft.org/resources/webinars.html. You can find announcements on upcoming ACM and SIGSOFT webinars and other ACM activities at learning.acm.org and www.sigsoft.org. That said, this is Bradley Schmel saying goodbye for now. Thanks again for joining us, and I hope you will join us again in the future.